This article looks at how steel belt coolers produce uniform pastilles. Cooling control, droplet stability, and dust reduction from a buyer's point of view. A useful starting point is this detail. A 5-factor matrix and 7-step checklist connect cooling control, droplet stability, dust reduction, and steel belt maintenance. From there, the video breaks down the specifications, supplier evidence, and risk checks that procurement teams should compare. A 5-factor matrix and 7-step checklist connect cooling control, droplet stability, dust reduction, and steel belt maintenance. Stable pastilles depend on more than cooling capacity. Steel belt coolers are often judged by throughput, belt width, or cooling area, yet uniform pastilles depend on a wider chain of process variables. A chemical plant can install a large cooling surface and still face dust, fines, broken particles, sticking, or unstable particle size if feed temperature, droplet formation, belt surface condition, cooling residence time, and discharge timing are not controlled together. For procurement teams, the central question is not whether the machine can cool molten material. The stronger question is whether the system can turn a variable molten feed into stable solids with repeatable size and low downstream handling loss. How steel belt cooling converts molten feed into stable pastilles. 2.1 Working principle of steel belt pastillation. In steel belt pastillation, molten or semi-molten feed is metered through a distributor and deposited as droplets onto a moving stainless steel belt. Cooling is applied through the belt, around the belt, or across a controlled cooling zone until each droplet becomes a solid pastille. The final particle is created before packaging, conveying, or storage begins, so early process instability becomes visible later as dust, fines, sticking, cracked pastilles, or uneven flow in bags and hoppers. 2 Droplet deposition, belt movement, and controlled cooling. Droplet deposition determines the starting geometry. Belt movement determines residence time and spacing. Controlled cooling determines whether the droplet solidifies from the surface inward in a stable way. If the feed is too hot, droplets spread and flatten. If it is too cool or too viscous, droplets may form irregular tails or incomplete shapes. If belt speed is not aligned with cooling capacity, the pastille may be discharged before the core is stable or after it has become too brittle. 2.1 Droplet height and spreading behavior. Pastille shape begins at impact. A droplet with stable volume, height, and surface tension can form a repeatable dome. A droplet that splashes, strings, or spreads unevenly creates inconsistent particle height and contact area. Buyers should therefore ask how the distributor handles viscosity change, feed pulsation, and temperature drift during continuous operation. 2.2 Surface tension, viscosity, and early crust formation. Surface tension and viscosity influence whether the droplet holds its form until the outer crust develops. Early crust formation is useful only when it does not trap heat unevenly or create internal stress. For how steel belt coolers produce uniform pastilles. Cooling control, droplet stability, and dust reduction. The safer decision is to compare the article's requirements against real supplier evidence, not only the sales description. Before purchase, teams should confirm the operating conditions, specification limits, quality checks, support expectations, and any trade-offs that could affect daily use.